In this video, we're going to do a one-factor repeated measures analysis of variance. We're going to use our example from our textbook, Statistical Concepts by Lomax and Housebohm. It's the second course. We're going to use repeated measures, and we're going to use it on the raters' raw scores, so we can situate ourselves in this data where we have both raw and rank score for each individual person. And we could say that they are rating an assessment or a quiz. This could be a quiz in their statistics course. I think the example they use is a writing essay. So someone evaluates, a rater evaluates each person. So rater 1 is going to evaluate person 1. And rater 2 evaluates person 1. And rater 3 evaluates so on and so forth. Rater 1 also goes down the list. So rater 1 now has evaluated person 1 through 8. Rater 2 has evaluated persons 1 through 8. Rater 3 is 1 through 8. Rater 4 is 1 through 8. So we have 4 raters reviewing 8 people. This could be 4 raters reviewing 100 people, 1,000 people, 1,000,000 people. We could have 2 raters. We could have 10 raters. We could have 20 raters. The more raters we get, the more difficult it might be in interpreting the difference. But we may actually have some need for those in some really large scale testing where assessment, judgment is necessary. So this simple repeated measures design is 4 different persons or raters evaluating our subjects. We're going to use the raw score data. So let me go ahead and get us started. Typically under Analyze we go to general linear model, but instead of going to univariate, we're going to go to the repeated measures. So here's repeated measures. We see another little dialog box pops up. We can name our within subjects factor. The within subjects factor is our repeated measures factor. So we have raters, so I'm going to call it rater. You can call it whatever you want. I have 4 levels because I have 4 raters. Rater 1, 2, 3, and 4. I'm going to go ahead and click add. Now this is the within subjects factor. My between subjects factor we'll talk about more when we get into some of the split models. I'm going to go ahead and click define. And we notice a new dialog box pops up, and there's all of our variables over here in the left hand portion of the box. And there's 4 potential variables we can place. We are only going to use the raw score variable. So I'm going to take raw 1 and place it in this box. And there's different ways we can do this. We can drop and drag, or we can select multiple at once and shift them in there. In the end, you just want to make sure you have rater 1, rater 2, rater 3, rater 4, and all of the raw values. You don't want to mix and match the raw and ranked values. And then from there, a lot of the things we would do are very similar to what we did in the random effects or fixed effects models, or mixed effects models. We have some options. We can look at descriptive statistics, effect size, observed power, homogeneity of variance. And I'll stop there for now. We can also look at the mean differences if we want to. I'll go ahead and do the Bonferroni test. Nothing new here. We could save our residuals if we wanted to. So if we wanted, we could save our unstandardized residuals. Sometimes we have done some work by exploring the unstandardized residuals for independence. In this case, we might not expect independence amongst our raters. Because there's 8 persons going across, so each person is dependent on themselves. We still expect each individual each individual person to be randomly selected from the population. We're not going to do any post hocs, but we'll take a look at some plots. In some cases with repeated measures, our plots are much more important, and that is because we'll be looking for a trend. In this case, we're not really looking for a trend. That is, a linear trend amongst the pattern of rater 1, 2, 3, and 4 doesn't really mean anything here, or a quadratic trend. And the reason why is because It's not like we're doing 4 different occasions and looking for growth. These are raters evaluating the same person. So the difference between them is nominal, not necessarily any ordinal expect or any trend expected. I'll talk more about that in a moment. We have no between subjects factors, so then the homogeneity test is not really relevant right now. So let's look at what our results are. We know we have 4 raters. Descriptive statistics, this is the mean value for each one of the raters and their standard deviation. The first thing we get is a multivariate test. These are multivariate f-tests. In our theory videos and classwork, we know that the multivariate test is a more conservative test, but we don't have to rely on the idea of sphericity. As a reminder, the idea of sphericity is very similar to compound symmetry, but it's less strict. We only have to worry about the variances in the model instead of the covariances. So basically that's similar to like when we did the assumption of homogeneity of variance, and that's what we're basically doing here in sphericity. I talk more about that in other videos, or another video. So the first thing we're going to do is we're going to look at the multivariate test. And there's 4 different multivariate Fs. In class, I teach you all that if you understand how to do significance testing, it shouldn't matter what the statistical test is. That is, you should be able to read that this is an F value, and in this case, we'll look at the Wilks lambda value, and go across and see that the F value for Wilks lambda is 48.65. And as we go across, we see that it is significant at the 0.05 level. We also have a measure of partial eta squared. This test, the multivariate test, does not require the assumption of sphericity. So if our sphericity weren't met, we would use this assessment. And we're going to use the Wilks lambda test, is what we're going to recommend of the 4 tests. There's different measures for the 4 criteria that if we get into more multivariate statistics in another course, we would talk more about. Also maybe if we get into some factor analysis and eigenvalue deconstruction we talk about, but not in this video. In our assumption of sphericity, we can review that and we can see whether or not it has been met, just like we did with our assumption of homogeneity of variance. And we can see that our chi is tested with a chi-square test and that it is 0.062. It is not significant. That means we have met the assumption of sphericity. We don't want this to be significant. Because this is not significant, we can actually use the more traditional univariate test if we choose to instead of the multivariate test. In this is our within subjects effects. We actually don't have between subjects effects, which is why, again, the homogeneity of variance test didn't pop up. Our test of within subjects effects, we have sphericity assumed. Well, we're going to go ahead and use that one. So we go over rater. We see that we're interested in the difference amongst raters. Sphericity is assumed based on our test of sphericity. We can see that we have an F of 73.47, and it is significant. All of these are significant. And when we look at them, the most conservative of those are the lower bound and the Greenhigh-Scalzer. And then finally, the Hund-Felt test is the most liberal. In general, we would usually use when sphericity is assumed, we use the first line here. If not, often I will also report the Wilks lambda as it is a conservative measure. As before, we've seen in our between group effects, whether it's random or fixed, we have partial eta squared. In this case, it's 0.93. And we have observed power, and basically rounded to 1. So our observed power is is there enough differences amongst the raters in this case to be observed if the difference really exists? And yes, we're pretty much at the maximum difference possible. I mean, of course, there could be larger, but the maximum difference we need to detect. We're going to ignore these for now. If we had different occasions and times, we could be interested in linear and quadratic or cubic effects, but we're not going to worry about those. Also, we have no between group effects. We only have the difference between raters on the same persons. We don't have different groups of persons, as we'll see in a later video. Finally, we have a couple other things that have popped up here for our effects of their marginal mean. We have the grand mean basically represented overall. We have estimates. These are effectively the estimates. We can see for our raters, we have rater 1, 2, 3, and 4. We have their means and standard errors. And again, we've talked about how confidence intervals in class. We've talked about the confidence interval band around the means and how that kind of gives us a look to see where overlapping variance may occur. Did a couple pairwise comparisons just if we wanted to know the difference amongst raters. So in this case, the difference amongst our raters, we can see just pair by pair. 1 and 2 are basically the same. We see that here as well. And then 1, 3, and 4, 2, 3, and 4, and then 3 and 4 are different from everyone. And we can see just like we would do with any sort of paired comparison test. And finally, we will jump down and look at our profile plot difference. We saw that there was a linear trend here, but that doesn't really matter. This is just rater 1, 2, 3, and 4. We could have called this person rater 1, we could have called rater 4, and rater 2 we could have called rater 3. So the fact that they're in a linear order really doesn't matter, but it still helps us look at them in space. And that's all I'm going to go over in this video for our repeated measures, our one-factor repeated measures analysis of variance. I'll put out another couple videos or another video or so on repeated measures and possibly doing some non-parametric tests as well.